Hi, so we are from group EE1111A. My name is Ziad Adam bin Osman and my student ID is 2021877588.
Hello, and my name is Muhammad Afi Akil bin Adenan. My student ID is 2021800882.
Hello, my name is Awang Akmal Reza bin Awang Putra Yusri and my student ID is 20218639F58.
So for today, we are going to present our calculus assessment 3 group project. We are from group EE1111A. Our group consists 3 members, which is myself, Zaid Adam bin Osman, Muhammad Afiq Akil bin Adnan, and Awang Akmal Reza bin Awang Putra Yusri. Today we are going to present about applications of differentiation, related rates. What is differentiation? Differentiation refers to the rate at which one quantity changes in relation to another. The rate of change of distance with respect to time is used to calculate speed. This speed at each instant is not the same as the calculated average. Speed is the same as slope, which is nothing more than the instantaneous rate of change of distance over time. Differentiation is defined as the ratio of a small change in one quantity to a small change in another that is dependent on the first quantity. One of the most important concepts in calculus is the differentiation of a function. Differentiation determines the maximum or minimum value of a function, the velocity and acceleration of moving objects, and the tangent of a curve. If y equals to fx and x is differentiable, the differentiation is denoted by f prime x or dy dx. Why do we use differentiation? Differentiation enables us to calculate rates of change. It, for example, enables us to calculate the rate of change of velocity with respect to time, which is acceleration. It also allows us to calculate the rate of change of x with respect to y, which is the gradient of the curve on a graph of y against x. As an example, differentiating x to the power of something. Number 1, if y equals to xn, the dy dx is equals to n x to the power of n minus 1. Number 2, if y equals to k x to the power of n, the dy dx is equal to n times by k and x to the power of n minus 1, where k is a constant, in other words, a number. Therefore, to differentiate x to the power of something, you bring the power down to in front of the x, then reduce the power by 1. As an example, if y equals to x to the power of 4, the dy dx is equal to 4x to the power of 3. If y equals to 2x to the power of 4, the dy dx is equal to 8x to the power of 3. If y equals to x to the power of 5 plus 2x to the power of negative 3, the dy dx is equal to 5x to the power of 4 minus 6x to the power of negative 4. Related rates. Related rates problems in differential calculus require determining the rate at which a quantity changes by comparing that quantity to other values whose rates of change are known. The pace of change is generally measured in terms of times because numbers in science and engineering are frequently connected to one another. Related rate approaches have a wide range of application in these domains. Because most issues contain many variables, differentiation with regard to time or one another of the other variables necessitates the use of the chain rule.
For the most common way to approach related rates problem is the following. First, identify the non-variable, including rate of change and the rate of change that is to be found. Second, construct an equation relating the quantities whose rates of change are known to the quantity whose rate of change to be found. Third, differentiate both sides of the equation with respect to time or other rate of change. Often the chain rule is employed at this step. Fourth, substitute the non-rate of change and the non-quantities into the equation. And the fifth is solve for the wanted rate of change. Our problem statement. For our problem statement, uh, we create a group of students went to a Legoland water theme park. They were assigned by their math lecturer to do an investigation on hemisphere tank available in the water park. If the tank is filled with water at the constant rate of 100 centimeter cube per second and the radius is at 80 centimeter. So the question is, we need to find how fast is the radius of the tank change and what is the rate of change of the tank surface area. Given that uh, the volume for the hemisphere are 2 over 3 pi r cube and the area for hemisphere is 3, 3 pi r square. For our problem solution is to find the answer for the question A, that is how fast is the radius of the tank change. We need to find the information first. Firstly, we found radius. The radius for the hemisphere is 80 centimeter and the rate of volume is 100 centimeter per 100 centimeter cube per second. So we know the volume for the hemisphere is 2 over 3 pi r cube. So we differentiate the volume. After we differentiate the volume, we differentiate r. That is, we know the rate of volume is 2 pi r square. So to find the how fast is the radius of the tank change is dr over dt is equal to rate of change for radius. To find that, dr over dt is equal to dr over dv times dv over dt. So dr over dv, we know that dv over dr is 2 pi r cube. So dr over dv is equal to 1 over 2 pi r cube, 2 pi r square, sorry. And dv over dt, we know from the information given that in question, dv over dt is equal to 100 centimeter cube per second. So dr over dv times to the dv over dt is equal to 100 per 100 over 2 pi 2 pi 80 square. So the answer is 1 over 100 128 pi centimeter per second. For the question B, the question is asking what is the rate of change of the tank surface area. This question is related to the question A. Uh, we know the area is 3 pi 3 pi square. So the rate of change for the area is 6 pi r. After that, we take the value from the radius. We insert into the 6 pi r, that is 6 pi times 80. After that, we found out that 480 pi is the answer for the dA over dr. In order to find dA over dt, we need to find the dA over dr times dr over dt. Since we find the dr over dt from the previous question, that is from question A, so we insert that dr over dt is equal to 1 over 128 pi. Then dA over dr, we found that the answer is 480 pi. So 480 pi times 1 over 128 pi. So we got the answer. The final answer is 3.75 centimeters square per second. This is the final answer for the question B. As a conclusion, in our related threads, two or more variable change at the same time, perhaps at different rates in a related rate issue. We can figure out how the variables are connected and how quickly one of them is changing if we know how the variables are related and how fast one of them is changing. This usually include constructing an equation linking the two variables and computing the equation derivative with respect to time. Often implicit differentiate is applied. So that's all for our group. Thank you.